To calculate oxidation numbers, we have some examples given to us here. So the first example is to calculate the oxidation number or oxidation state of the species that is unique. This is the compound known as potassium dichromate, potassium heptaoxodichromate 6. So we are told to calculate the oxidation number of chromium in that compound. What is the oxidation number of chromium? So chromium is in yellow, so we are told to calculate the oxidation number of chromium. Let's look at the other compounds. We are going to be calculating the other compounds. So we have 5 compounds in all, or rather 5 substances, because number 2 and number 3, even number 4 are all radicals. So we are going to be looking at how to calculate the oxidation state or oxidation number of the elements in yellow. So number 1 is chromium, number 2 carbon, number 3 phosphorus, nitrogen and sulfur. So we have seen the rules that governs calculation of oxidation number. Let's go through these rules again just to remind ourselves what was said. Look at the rules. We are told that if we are trying to calculate oxidation numbers, let's look at the first one. We are told that the oxidation number of an element in an uncombined state is 0. That of group 1, 2, 3 are plus 1, 2, 3. And oxidation number of hydrogen is plus 1 except in hydride. But let's look at the sixth rule here. It says that the sum of all the oxidation numbers of elements in a compound is equal to 0. So if we are told to calculate the oxidation state or oxidation number of any element, as we can see in these examples here, the first question says we are to calculate the oxidation state of the indicated atoms. The indicated atoms are the ones in yellow. So chromium is the first element we are to calculate its oxidation state or oxidation number. The name of that compound is potassium heptaoxodichromate 6. That's the full name of that compound. For short, you can say potassium dichromate. But the full name is potassium hepta. Hepta is 7. That is 7 oxo. Potassium heptaoxo. Hepta is 7. Oxo stands for oxygen. That is, it tells us that there are 7 oxygens there. Potassium heptaoxodichromate 6. The question is, why is it dichromate 6? Why that word 6? That value 6. Why the number there is 6? Why is it not 2 or 3 or 4 or 5 or 10 even? Just as we have tetraoxosulfate 6, we have trioxocarbonate 4, we have trioxonitrate 5. So when we have these compounds that are called and some numbers are being attached to them, the question is, why those numbers? When I say trioxonitrate 5, why 5? Why is it not 3 or 2 or 9 or 8? Why 5? That is what we want to look at. So those numbers that are attached to the names of certain compounds are obtained not by chance but through what we are going to do now, and that is what we call oxidation state or oxidation number of that particular element in question. So for example 1 now, the name is potassium heptaoxodichromate 6. Let us see why that name dichromate 6 is attached to it, because we have to calculate the oxidation state. Now the oxidation state of potassium is +1. Why do we say it's +1? To recall our electrochemical series. So you can see, dear students, like I told you from the beginning of this class, that electrochemical series is so important that we need it in very many things we'll be doing in chemistry. So you have to always recall your electrochemical series at every point in time. We saw in the electrochemical series or activity series that potassium is 1. In fact, potassium is even the first element we started with. So its oxidation number is +1. Potassium is +1. Chromium is what we are looking for. There are 2 chromiums there. We don't know the oxidation state of chromium, so we are going to put it as X. Then oxygen, oxidation state of oxygen is -2. So, but by the time I have solved 2-3 questions, you will get to know that oxidation state of oxygen is -2, potassium is +1, chromium is unknown. So how do we go about that? The compound is K2Cr2O7. And we are told that the oxidation number of a compound like this, we just equate it to 0. So if we are to solve this now, this is going to be, since oxidation number of potassium is +2, and there are 2 potassiums there, so this is going to be 1 times 2. Plus, the oxidation number of chromium is what we don't know. We are trying to look for it, so we're still going to leave it as Cr2. Then, plus, the oxidation number of oxygen is -2, but there are 7 oxygens there, so it's going to be 7 times -2. 7 times -2. All equal to 0. So this is going to be 1 times 2 is 2 plus Cr2, which is the same thing. You can still say 2Cr or Cr2. But let's just leave it as 2Cr2. Let's leave it as Cr2. Let's just proceed. We shall get to see something later. Cr2 plus 7 times -2 is -14. All equals 0. So this is giving us 2 plus Cr2. Minus times plus is minus. So this gives us -14 equals this. So this gives us 2 plus Cr2 equals 14 as we take it over to the other side. So our Cr2 is equal to 14 minus 2 when 2 go over the other side, and that gives us 12. So it means that our Cr2 is 12. But we are not looking for Cr2, just like in mathematics where you solve and you have x equals 9, s squared equals 9. You're not asked to find s squared, but what you're asked to find is x. So it means that x is now going to be square root of 9, isn't it? So this is actually the same way to here. We are not looking for Cr2, we are looking for chromium, chromium. So to solve for chromium then, we have our Cr2. So what we simply need to just do is to divide by 2. That's what we just need to do there. So let's look at that. Let's lift that up a little. Okay, so we have this. So to look for our chromium, therefore, we're simply going to say it is either you write it 2Cr or Cr2, whichever you wish to do. So to do that, we have over 2 and then 12 over 2. So when this cancels that, 12 over 2 gives us 6. So this is actually how chromium is equal to 6. So you can see that is why the name of that compound is potassium heptaoxo dichromate 6. Potassium heptaoxo dichromate 6. That is the name of that compound. So this is how to calculate oxidation state or oxidation number of elements in a given compound. We look at the next one, CO3 minus 2. CO3 minus 2. CO3 minus 2. We have a law that says the oxidation state of any compound is equal to 0. But when it is in the ion, that is like the radicals we can see now, we equate it to that charge of the radical. That's what we are saying here. So looking at it, this is CO3 raised to power minus 2. So instead of saying this is equal to 0, we'll simply say it is equal to minus 2. So we equate the whole compound to minus 2. That is just what we need to do there. So this is going to be this charge, the charge that the radical is having, that is this minus 2. We'll just bring it down here and equate everything to minus 2. That's what we need to do. So we simply rewrite it as CO3 is equal to minus 2. So that's just what we need to do. It's as simple as that. Then we'll now carry out our calculation. The question says we should calculate the oxidation state of carbon. Carbon is what we are interested in. So since we are interested in carbon, what is the oxidation state of oxygen? Is -2. Since the oxidation state of oxygen is -2, how do we know it's -2? When you remember the electronic configuration of oxygen, oxygen is atomic number 8. 2 electrons will be inside and 6 electrons outside. It needs 2 more. So when oxygen gets 2 more electrons from any element, when it gets 2 more electrons from any element, that is actually what makes it -2. It always collects. But if you remember, potassium, for example, as we saw here, was +1. It is +1 because potassium will always give out 1 electron, just like sodium. So when you give out electrons, you'll be plus, but when you receive, you'll become minus. So that is why oxygen is -2 in this case, and always -2, except in peroxides. That's why it is -1. So now we are looking for the oxidation state of carbon. Oxygen is -2, we know. So this is going to be C+. Since oxygen has oxidation state of -2, but there are 3 oxygens there, so this is going to be 3 times -2. Close the bracket, all equal to -2. So this is going to be C+. 3 times -2 is -6. All equals to -2. So this is going to be C+, or rather C-, because minus times plus is minus. Minus times plus is minus. So this will be C - 6 equals to -2. So C will be equal to, when 6 go over the other side, so it will become -2 plus 6. And C gives us, -2 plus 6 gives us +4. I want to believe you know that. So this gives us 4, or +4. So we can see the oxidation state of carbon is +4. And that is why that CO32- is called carbonate 4 ion. Carbonate 4. Just like why when we have a compound like this, CaCO3, for example, this is called calcium trioxocarbonate 4. Carbonate. So you can see that carbonate 4. This is also called, when we have this, zinc, this is called zinc trioxocarbonate 4. Potassium trioxocarbonate 4. So you can see all these carbonate salts will always end in 4. Carbonate 4. So that is actually why carbon is having oxidation state of 4 in carbonate salts or carbonate compounds. So this is actually the reason. So when we have compounds or radical that has charges, we equate the whole species to the charge. The next one is also similar, PO4 raised to power -3. So we are told to calculate the oxidation state of phosphorus, P. To calculate the oxidation of phosphorus, P, let's proceed. PO4 raised to power -3. PO4 raised to power -3. What do we need to do? Simply, we equate the whole thing to -3. So we can write as PO4 now equals to -3, just for clarity. So we are looking for phosphorus. So phosphorus is going to be P plus. Oxygen we have been told is -2. We have seen that is -2. So this is going to be P plus 4 times -2 equals -3. So we can solve here. So this gives us P plus 4 times -2 will be -8 equals -3. So this will become P plus times minus gives us minus. P minus 8 equals -3. So P will now be equal to, when 8 goes over the other side, it becomes -3 plus 8. So our phosphorus, the oxidation number of phosphorus will now be 5, plus 5. If you wish, you can write plus 5 or just 5. So it means our phosphorus is 5. That is plus 5. So this is how to calculate oxidation states or oxidation number of elements. The fourth one is nitrogen. We are asked to determine the oxidation number of nitrogen in ammonium ion. Ammonium is a radical. Ammonium ion, NH4 raised to power plus 1. Ammonium ion. So to do that, the same way we have been doing, we'll simply so to do that now, this is ammonium ion plus 1, or we just say plus. It's needless putting 1. Plus is enough. We know it's 1. So since we are looking for nitrogen, this will now become NH. Here will become NH plus NH4 is equals to plus 1. Now we can write our 1. Since we have been told that when we have radical species like this, that everything will be equated to the charge. So hydrogen we've been told that is having oxidation number of plus 1, except when it is in hydrides, like potassium hydride, sodium hydride, calcium hydride. Then it has oxidation number of minus 1. But normally it is plus 1. So in the case of this is going to be nitrogen plus, hydrogen is plus 1, but there are 4 hydrogens there. So it's going to be 4 times 1, all equals to plus 1. So this is going to be n plus 4 times 1 is 4. So this is going to be n plus 4 equals to 1. So to get our nitrogen, this is going to be 4 going over the other side. This becomes 1 minus 4. So our n is minus 3. Our n is minus 3. So the oxidation state of nitrogen in that compound, that species, is minus 3. That's the oxidation state or oxidation value of nitrogen. The next we have there is lead sulfate. Lead sulfate. So lead sulfate all equal to 0. From our electrochemical series, lead is plus 2. Sulfur is what we are looking for. Plus oxygen. Oxygen is minus 2. But there are 4 oxygens, so it's going to be 4 times minus 2. All equal to 0. So this is going to be plus 2 plus sulfur plus 4 times minus 2 gives us minus 8. All equals 0. So this gives us plus 2 plus S. Plus times minus 8 is minus 8 equals 0. And here we have plus 2 plus S. When minus 8 goes over the other side, it becomes positive 8. And to get our sulfur now, plus 2 can join the other side. It will now become S equals 8 minus 2. So we have 8 minus 2. So S will become positive 6. And that is why the name of that compound is lead tetraoxosulfate 6. Lead tetraoxosulfate sulfate 6. So this is how to calculate oxidation numbers. So with that, I want to believe we are very clear about calculations involving oxidation numbers, and we can calculate any oxidation state or number of any given element. So with that, I leave you there, students, now with this. This is your STS, students to solve. So go ahead and solve the following questions. You have to solve for the oxidation state of the elements in yellow. So that is to test our knowledge of comprehension. So we have seen that. So we are going to proceed to our next subtopic, and that is called balancing of redox reactions.